All right, greetings everybody, and welcome to these project presentations from the ML Verifiability Hackathon that happened the past weekend from May 26th to May 28th. We had a lot of signups, but only 3 entries, and it might have been because the topic was quite hard, or that we were missing some keynote speaker that cancelled. But now we do have 3 great projects available that we want to check out for this project presentations. So one is by me, I was working a bit in London, and another is by Brian Mohe, and another is by Matthew Eva and Giles Atkins. So I will go first and jump straight into it, and then we'll get to the next projects. So first off, this fuzzing large language models, a framework for discovering edge cases. It's basically a small prompting framework that was developed to sort of fuzz large language models. And fuzzing is this concept where on a high level it is repeatedly running a program that generates inputs that may be syntactically or semantically malformed. So basically tries to figure out the places where a program fails by just providing it with a bunch of input. And this can be a lot of different inputs. Of course, for language models, we expect it to be language itself. So in a more formal definition, it is execution of program using inputs sampled from an input space that protrudes the expected input space of the program. So this protrusion is that it goes beyond what we expect the program is able to handle. And this, of course, with language models might be cases where the training data doesn't actually cover it that well. Maybe, in long sequences of text that have never occurred on the internet, it wouldn't be able to actually generalize properly. Or in some cases with code, not understanding the actual semantics of the code, but just memorizing or just regurgitating what it has already learned. And one of the very interesting things in regards to large language models and neural networks is this white box fuzzing, where we understand the internals of a program. So in this case, that's a neural network, right? And when we then understand the internals, we can use it to generate these fuzzing examples. So in this case, we might use mechanistic interpretability or interpretability more generally. And this is often slow, but quite interesting in these neural network relations. So therefore, a lot of fuzzing happens black box, or it's also called IO-driven or data-driven testing. And this is basically where you assume you don't have access to the internals, and you just throw a lot of things at it, get some output, see, okay, does this make sense? Does this actually fail the model itself? And in this case, we want to apply fuzzing to large language models and use large language models to generate the examples themselves. And for AI safety, this is of course highly relevant because these unexpected behaviors of the language models are super important to find because there are a bunch of risks associated with exploiting vulnerabilities and misbehaviors that happen at the edges of what it has learned. There are some versions of the alignment problem which are basically defined as avoiding any sort of out of distribution error. So yeah, in cases of for example, Rumbelow and Watkins, from this year, they showed that some tokens can be semantically completely misinterpreted by a network due to the structure of the training data itself. In the tokens that are very either like used in a very weird way online. So in their case, it was, for example, solid gold magic harp, which was misinterpreted as another word entirely, and they traced it back to in the training data being because of a Reddit user or something like that called solid gold magic harp. So these are the kind of edge cases we expect to find with this. And of course, white box fuzzing is stuff we can do like the solid gold magic harp case. But white box fuzzing also presents some of the next steps for something like black box fuzzing of language models. So some existing work where they've used fuzzing or where they've used large language models to create fuzzing is in this Deng et al. From 2 different papers where they use LLMs to generate code examples, basically to test deep learning libraries. And I think they found like 47 new, never before seen bugs in the deep learning libraries using just the language models to, with this great overview of their design, using the language model to generate new examples of code that might bug out the libraries themselves. And another piece of existing work is, of course, automated red teaming. So Perez et al., they used LLMs to generate these adversarial texts designed to elicit the harmful responses. And this can be to some degree seen as fuzzing, but in this case it's very focused on these like outputs that are non-intentional or like, for example, harmful. Well, what they describe it as is a harmless, honest, and helpful language model. So it's the reverse they are trying to catch here, and then train against that. So what did we do? Well, first of all, we used the new RWKV architecture from Elude AI, which is a 14 billion parameter recurrent neural network, which is quite interesting because that's of course not a transformer, but they've been able to train it really efficiently and then use some of the capabilities of RNNs. So tried experimenting a bit with that. And then we basically have multiple prompt histories. So H1 is not hypothesis 1, that's history 1. So that's composed of the prompt 1 input and any output from the first model. And I think it makes more sense to look at the actual figure of it too. So I'll probably just explain it in relation to that, which I think is here. So you see that the prompt 1 is an instruction for creating an adversarial input or an adversarial prompt, which M1 is then the adversarial model that creates the prompt. And that sends this input to the target model, which is the one we want to fuzz. And then we have an annotator model or an expert model that looks at the output given the input and then tries to classify the surprisal or how surprising that output is on a scale of 1 to 5. Like, do these actually fit together? And then you can see on the right is the data set that comes out of this when you run it automatically. You basically get the prompt plus output, of course. You get the actual surprisal on these scales. So that can be any property in reality. So that can be whatever M3 is designed to classify, like safety or weirdness or like harmfulness or something like this. And then the third item is this white box fuzzing principle where, we can actually save the activation to because we have access to the neural network. So we can save a lot of things here, and some of the further design, some of the next steps, I'll also detail on another slide, but it's basically taking some of this neural network activation data and seeing, okay, how does activation change on this scale of surprise? Well. With that framework, it's like some of the good steps towards automating this fuzzing on language models, and we didn't get to a state where the results were possible because I was in an airport and running the hackathon. So we did find that the 540 million parameter RWKV is not at all capable enough to execute or evaluate fuzzing, and that the P1 prompt is quite important and will probably benefit from some chatbot RLHF step. So that's the same sort of interaction scheme you see with ChatGPT, which has been trained on that. And then this 100-line implementation of RWKV we used might be too simplistic for this specific scenario. And some of the next steps are to do the steps manually, just like checking out, does it actually work with a super powerful model? Run it using the GPT-4 API and see if the outputs make sense. You would expect GPT-4 to be much better at doing this sort of thing. And save the activations of the network while running each fuzzing attempt as well. And you can see a bunch more like how we might use the activations and whatnot on the actual repository at smkc/verificationjam. So, do we have any questions for this? Yeah, so basically in this case we use the same model architecture, and I think this comes back to, it's also detailed on the repository, but like an evaluation step of do the outputs make sense, right? Because you have a case where something like solid gold magic carp, if the annotator model and the target model are the same, then the annotator model won't actually be able to annotate it as weird because it sees the same thing, or like, yeah, it sees what you would expect to see. But that is the good part of this, right? You can just use a bunch of history instances of prompt histories of GPT-4 and then try to make it work from there. Yeah, I mean, I think the interesting part here is that depending on how you prompt a model, its responses are going to change drastically, right? You have an infinite output space there. So it's basically you would expect the annotator model to catch most edge cases, even if they're very, very weird, because even though it's the same model as well, because you instantiate it with another prompt, right? So in that sense, you can say, okay, well, can we just fix the adversarial outputs, like target model's failed outputs, by giving it some chain of thought or something like this to make it more conscious of itself? But that is sort of what M1 is designed to do, like make it fail, right? Sorry, can I get the question again?
Repository of such information that people have voluntarily uploaded, stuff like that.
So I mean, in this case, we would at least start. I didn't find any specific prompts online that can elicit this sort of fuzzing attack. But jailbreak chat, for example, like jailbreakchat.com, can be a case of this, of like diving into it. But I mean, that's like sort of next steps of all this, right? So that would be the setup. Yeah.
Okay, cool. Thanks.
I think we'll jump straight to some of your wonderful presentations now.
Sure. So one, pause a moment while I explain. So first off, the idea behind the project was that machine learning models are very complicated. They have billions of parameters. They are connected in complicated structures. They have many layers of many dimensions. The idea behind the project is that if you want to understand something complicated and you want to be sure that it's doing what you want it to do, that it helps to have as much, like, to be able to absorb as much information about that structure as you can, have as much of your sensory bandwidth be filled by this by information about this thing as possible. So whereas usually we are limited to flat computer screens, we built Giles and I built a VR machine learning model visualizer. We targeted the Onyx open source machine learning model format for extra compatibility. I recorded a demo of it working, so I'll show that. So this is Onyx Explorer, a VR in Unity to explore visualize machine learning models stored in the Onyx open source file format, which is designed to store machine learning models.
We have layer, and so forth. Some of them are different sizes, as you can see. Some of these show connections between them. In theory, they all have connections between them, but we were having trouble with some of the connection formats. So at the moment, you only see some of them, but that does let you see kind of the inside of these things. It's when there are this many connections, it gets pretty tough to see what's going on. That's one of the things it's on the to-do list, to deal with how to make sense of all this jumble when there's just so much.
Yeah.
So down at the far end, as you can see that the model changes as it goes along. While each of these are layers, you can see that they're of strange sizes. That is, we've projected that layer's element tensor into three-dimensional space. And so the projection can make it go in strange angles. Because we only have 3 dimensions to work with. Down here, I think this is the MobileNet's an image classifier, so I think this one is probably the output layer. Because it's a tensor of just one in every direction except for one direction, which it is really long. Now, I'm going to stop this for the moment, and I am going to basically turn off
Yes, VR code editing. I assume you wrote it all like
whatever
this.
you call it. Oh no, turning off the connections basically. Right. So let's see. Back to Unity. It'll compile for a minute. Go. And what I realized is that I think I probably moved the VR view out of your line of sight when I went back to Unity when I started this up. So you may not have had the best view of that the first time around, but this should be better. So again, we have layer, and there's no connections displayed this time around. Again, you can see the image that we had put through this this model is a cat. So yeah. Thanks for listening, I guess.
Let's see. Can you hear me again?
Yep, we can.
Cool. One detail I noticed I may not have or stated clearly was that the colors there were the activations of the neurons. So if you could see faintly, there was the image of a cat in some of those early layers, which got a little bit distorted as the model progressed. So that was what that was.
Yeah. Awesome.
Further, there were some things that we tried to do didn't quite work, and so further improvements might include things like fixing the neuron highlighting. For a brief moment, I had your controller on it would show you that neuron's connections. It would like highlight them in red and blue, but then we switched rendering systems to be significantly faster, and that stopped working. So other things that could be improved, like additional support for additional types of Onyx layer. I think that it would be useful to, for instance, outline a layer in the type of layer that Onyx says that it is. For instance, a convolutional layer, an addition layer versus sigmoid layer versus something else. Like maybe they could be color coded, because as I mentioned, there's just so much information there. Like if you display all of the connections at once, it turns into a solid block of color. So other ways of dealing with that, maybe like, I don't know if merge is the right word. I feel like there's another word, but like, show if multiple things connect to the same things, you can join their connections and just simplify the display like that. And so forth. Other like clicking on neurons and what they're connected to, or manually activating neurons and seeing what results it has, and so forth, might be other improvements that could be added to make it a more useful analytical. But yeah, that's what we did.
Nice, rock and roll. Well, let's give him a hand with all the emojis. Awesome. I guess open for questions now. Something like I'm curious about how this relates to safety verification, right? Because there's one way where I imagine with this you could imagine like a neuromancer-like future where the verification people in like governmental agencies, they dive into the models and go around them trying to find biases or whatever in some weird cyberspace. What have you thought yourself about this specifically, or is it mostly a visualization tool?
I mean, that's sort of the idea, is that, like, in my experience as a programmer, the better tools you have expecting stuff, the easier it is to understand what's going wrong. Like when I'm programming and all I have is console.log, it's very tedious. But if I can pause the debugger and inspect code and change variables and stuff like that, it gets a lot easier. And so similarly with machine learning models, if you can see what it's doing and poke at stuff and be able to get a better visual understanding of how things are laid out, then one would hope that you'd be to find problems and to understand why things are happening the way they are and how to get them to happen the way you want.
Yeah.
Other analytical algorithms could be plugged into this framework so that you can select this layer and this layer and this layer and run some kind of differential whatever on it.
Yeah. So yeah, it could be expanded into actual formal verification. You like search for the things you want to focus on.
Sure.
Awesome. Nice.
I had a question. So this is really wonderful. I've never imagined a neural network looking like such a weird object, but there it is. It's a really weird object. It's a mathematical object. So, my question is, when you're talking about, so you're visualizing a cut, so like you can visualize a transformer, I'm assuming, with text passing through it. So is it possible to find to visualize like basis dimensions, or to visualize the residual stream at inference time?
When you say basis dimensions, I was honestly, I was more the I think we both learned a little bit about each other's area there, but like I mean, the encounter I had with basis vectors was in the context of tensors having like needing to project tensors down into three-dimensional space, but I'm not sure that's the basis you're talking about.
So it could be, I mean, so basis dimensions, they're literally just in any one of those embedding vectors, it's like a subset of them. I'm saying, you want to imagine if you have one that's very, you can imagine a histogram that's speaking there. That's the kind of thing I'm thinking. Like if you want to find, based on text or something in some narrow dimension, you find something which is speaking, and then you can use that to highlight the text. Like I've been watching the series of interpretability videos that Anthropic published in December 2022, I think 2021. So I'll share links because they're really cool. Like they talk about info-weighted attention patterns. The idea that you can like highlight the text based on some value, and you can use different attention heads. Like you can use hooks on different attention heads to identify what in the text you want to highlight. So you can imagine if you wanted to visualize those specific heads in the layer itself, inside the network itself, as you observe it.
So what's your question?
So like,
or were you just suggesting a cool thing?
yeah, that's suggesting a cool thing we want to look at. Like if I had, yeah, exactly, like had like an implementation of this running, those are some of the things I would like be trying to see.
Okay. Yeah, I mean, if you can figure out a way to display it, then you could add the rendering capability into the code. I didn't say it out loud in the presentation, but there's we put the code up on GitHub. So if anybody wants to download it and try it, they can do it. You can post a link in the chat if you want.
That's awesome. I have a VR headset at home. I might try it out. Navigate some neural networks.
So here are the Anthropic videos.
Yeah, I also posted actually a thing I was made aware of, attentionvis.com, which is like a 3D visualization as well. Maybe I think it's 3D, where they basically do like the semantic embedding space visualization sort of thing, and then the relationships based on attention in a transformer. So super cool.
It's just this is the kind of thing in the past I've feel like once you have something working, then you can go back and add the features you want. Like once you have the ability to render, highlight colors and hover over stuff, and just makes a good platform to add functionality to. So
Yeah. Yeah, then the ball gets rolling from there. It's quite exciting too. All right, thank you very much for that presentation. Brian, do you wanna do your presentation now?
Yes, I will. Let me see. The context is I started in November. I started a language model company like a GPT-3 style like API, and I was basically doing basically trying to find ideas for how to design the querying. So like I was looking for reading documentation and different kinds of things. I'm like, so I want to design something that asks questions and I want to make the answers robust somehow. So I developed a few agents and then started building the user interface almost immediately. And then so it's been 6 months now. I've been like building the user interface and different related systems and all that. And a lot of the time I've been thinking about all the underlying issues relating to like data quality, like answers coming back correct and all of that. Just seeing the interface and seeing the data that comes back and thinking if it was actually like give very targeted feedback on each a sub answer or each subsection of the answers that I'm getting from the system, then maybe I can design a reward scheme that really that A learns from very little data and B really learns like not to bias answers or to like you can figure out how to verify different systems. So for the past week or so I've been kind of on a break, so I've been thinking about things, and like this hackathon was actually a good opportunity to like formalize things. So yeah, so this is what this is now. Thinking about like empirical systems, like some systems are in production and some of them are just theoretical. I've just like thought about the graphs and talk about how to deal with them, and then just to figure out if you can have a notation for describing these kinds of systems, so that you can talk about them and plan them and before implementing, so that like and I think it's possible to do it. Like think about the graphs this week as I wrote the paper. It occurred to me that it actually might work as a notation, but you just have to like explain it well so that people can accept it as a language they can use. So yeah, so this is what process-based supervision is. Like the idea is like you're using chains of language model calls, parallel calls, sequential calls, to add extra context and to answer questions and to do things that the first agent couldn't do or it doesn't have enough information to do. So we take it's like bringing two fields together, or at least we're trying to bring causal incentives. The idea where we can understand the incentives of agents, like you can understand the incentives of one agent and discuss it, or you can understand the incentives of multiple agents collaborating to do something. You can understand them by drawing these diagrams called causal incentive diagrams, and you can think about how to do the implementation formally before actually writing code. You can just think about different pros and cons, different kinds of strategies you might want to include, things like that. So you want to think about all of the processes and the effects those processes have on each other, because the system itself has it's an acyclic diagram. It's a graph. So you can analyze graphs mathematically, you can analyze graphs visually. There's many things you can do. So you want to have from any implementation of one of these language model chain systems, we want to like get the graph, the causal graph that they create when you execute it, and then visualize that causal graph. We figured like how to visualize that causal graph dynamically. Like whenever someone asks a question, you can generate that graph and see some nodes in that graph are okay or not okay. Maybe we shouldn't trust this answer. Just like looking at the graph, maybe you don't have to look at the answer itself. You can just look at the graph and the image and see if that's possible. So what I'm describing is a future vision, like, and this is just the first part of it. We're trying to formalize the first part of this. So we can have a common language for talking about things, to make sure that the language doesn't miss out anything. So it's been 3 days since I started the paper, so like want to verify that the language is actually useful for something before going too far. So the idea is like eventually this is going to be a user interface. Like we want to see in a Jupyter notebook style something gives you for the chain of language model, the calls that are done, graph that we get to visualize it. So right, so if you want to try this yourself, you should install a library called PySeed. Yeah, it's pretty cool, easy to use. So the talk is kind of mostly a tutorial on PySeed. So like there are all these graphs that you can talk about. So it's fine. You can just walk through that now. So I've gone through the supervision stuff. You want to call multiple agents and have each agent send data to another agent, or you want to formally describe these situations. So we'll describe the causal influence diagram first, because we'll be looking at them. It's a graph, a directed acyclic graph. This is a type of graph that it has no loops. It's just going in one direction. And then we have decision nodes represented by rectangles. This is a decision node. And then we have utility nodes represented by diamonds, O. So a decision node, you can say, is a model. Like it gets input and decides what comes out. Then O, a utility, is you can think of as reward. Like the moment where the model outputs its response and the user presses the thumbs up or thumbs down. So that's the agent gets utility, or the whole system gets utility. So yeah, the whole system gets utility. So then conditional probability distribution. And chance nodes represented by ovals. Chance nodes are I and C. So the idea here is the user input or the intent of the user is chance, right? It's a random thing, right? It can be positive, negative, it can be adversarial, it can be actually directed to what the agent is designed to do, things like that. And then C, the context, is also chance, because the user will do something that provides context context to the model. That process may or may not be trustworthy. So it can provide anything, really. So you can imagine a search engine where the ranking is broken, and C provides the wrong documents for the answer, to support the question, right? So it has a causal effect that may be positive or negative. And then M1, of course, is causal, like it causes the answer to come out. So yeah, so we represent models, context, user input, and the output. Then, okay, so this describes a single interaction, right? So you have one user, I. They have a question that they ask. They ask the question. The contents of the question are sent to a search process that in a database that returns graphs as context. And then the question is also sent to the model. The model receives both the context and the question, and just one agent. It's the simplest case because so this could be green in case of a correct answer. It could be red in the case of a correct answer, right? If you are coloring nodes in that way.
And then so the context, would that, for example, be like, is that the output of your program, or is that the output of, for example, like Bing getting a search result as well?
So when you ask Bing a question, when you ask Bing Chat a question, it starts a search process for paragraphs or for websites or for something, and then it sends those results to the language model, and then the language model abstractively summarizes, does something, and then outputs the results. So C is the first process. Or rather, I see the path I see. Look at the path here. There's this path,
Yep.
right? That's that process, right? The user ask the question, and the first thing that happens is we search pre-existing domain for knowledge.
Okay, would you mind explaining the meaning of the direction?
Okay.
Direction of the arrows.
Okay, the direction of the arrows. Okay, so imagine this is the prompt. So the prompt from the user is causing the what is in the context, right? The prompt from the user is causing what the model sees, right? And the context is also causing what the model sees. So it's like, you can think of it as information flow or data flow, right? You have entities that get data flow in, and you have other entities that output data flow, right?
Can you give an example of what you mean by context?
So let me use the interface so that you can see. So you can see that interface. Okay, cool.
Yep.
So this is digest the service that we're describing here. Some of the agents are actually implemented here. I'll talk about the 2 agents that are implemented in this right now, and then the others are just theoretical. So this is the context from the documents. You have a document here, PDF document, and then there are paragraphs from that document, right? So in order to answer this question, what the system had to do was find context paragraphs first, and then send them to a filtering process that cut them down to, they're cut down to 3. Let's say they're cut down to 6 or 10 or something, right? By a filtering process. So this is what the entire chain of models actually sees in terms of C, right? Then you have the user's question, and then you have the answer that came from the model, right? So you could say this is O, this answer is the O node, this is the I node, and this is C, all this, right? So whatever it is that the model gets to actually observe is I and C in this case.
Wonderful.
So do you understand that? Okay, cool. So let's see whether there's anything I haven't explained here. Okay, so that's correct. That's all finished. So this is the single agent case. It's the simplest case. If you want to have if you want to ask any more questions, can ask, and then before I move to the complex ones, the multi-agent ones, because they'll increase in complexity.
I think I'm good for now.
Okay, cool. So I've already explained why we would want to try this. Like, you may get a more robust result because you have multiple filtering steps. Like S-Band's fuzzing example is a clear version of that. Like, you want to have multiple agents that have been prompted to do different things, or to amplify whatever result has come in or something, right? You want to like have a thing like that, but you want to understand the positive and negative cases. Let's say you want to like think about those cases ahead of time and see whether you can design or something. So these are 2 simple cases. Actually not only 2, actually there should be 3, because we have a 4 agent scenario. So so here's one version. You take a pair of it. You have an agent, and then you instantiate a second agent. So you have M1. It's described there. The user input is here, right? They send the request to the database to find data. They'll send their prompt to the system. M1 is instructed to generate one extra question, right? And then M2 is instructed to take the user's. It's instructed to take. It's actually not instructed to take the user's input, right? It doesn't have the user's input, but then all it has is the context and the answer that M1 gives, and says, given this context, expound it or something, or like verify that it's correct, right? So that's the case, right? That's how let's say someone has designed a model to do that. So Cool. The challenge is, I'll describe it here in the text, but I'll talk about here, is that there's a missing link here between I and M2. So the I M2 is missing. And what that means in this like how we're describing things is that the user's input or the context was not relevant for this model. Like the model couldn't take it into account in this case. So it has no information about what the user originally asked. So whatever it gets in terms of information is context. Sure, that's data about the world. And it gets whatever M1 tells it, right? So if M1 made a mistake, or if it's hallucinating or whatever, if it's out of distribution for the context and the user input, it will misinform the user, right? So that's what we're going for here. Like we're trying to describe the situation where it doesn't take into account the user's context, the user's original question. And so for the rest of the description, I'm trying to describe an alignment failure as that, where there's no link between I and the M, any of the M's. It's like possible, like not a direct alignment failure, but there may be potential for it. Like it's more likely that it'll happen in that case.
Yeah, I guess you can also model M1 here, right, as a context node in theory, just that in this case it's an AI instead of like a search query or something like this.
Yeah. So the search query is IC, right? But this could also be another search query. Yeah, you're right. It could also be another search query. So, because it's certainly true. But I'll describe cases when the model itself can search the database. So this can be the user's context, and then the model can also look for its own context. Mm-hmm. But I'll describe cases later, and when it's more clear where we're going. So how do we fix this? We fix this in the diagram, at least, by adding this node, right? So that we're describing an agent that in all steps of operation takes in the user's intent into account. So we add this by just adding this IM2. It's like this point. And then, this is what it looks like. It looks balanced. At least you can see there's nothing missing visually. So when I was writing this, I was actually realizing that I was actually debugging this visually. I was thinking if I've missed a link, I can actually look at it and see, is there something that is missing? And I could actually notice that it's actually an issue.
Nice. So that's one of the benefits of being able to see stuff. Yeah,
exactly. Yeah. You can just notice instantly that that point was missing, and you need to rebalance the graph. So this case, I think we can use this case to describe the fuzzing case, right? Because if you look at the image that you had, Espen, like the graph that you had.
Yep.
So if you imagine a third agent here that maybe you're calling that the input model, and then they have the verifier, and then the prompt surprise or checker, right? So you have one input, it outputs values but the output from the first model goes to the second model, and it's prompted based on the question and the context. Is this correct? Based on the question and the context, is this correct? Or something like that.
Yep.
Then
that's a nice way to
so they
visualize it as well.
You can visualize. I think you can visualize it. So let's actually talk about that in the three. But then the other thing is, that's one useful factor, but a risk factor is that an error in M1 is piped to M2 directly. Right? So unless this model is like robust, unless it's designed in such a way that it should do a check, if it just accepts it and does something, that M1 can introduce an error to M2. And then that goes straight to the output. So the user is deceived.
Yeah. I also think you might have to jump a bit fast through the rest just for a time.
Okay, sure. So let's see. let's find this one. This is a third case which is similar to the verifier, but it has parallel agents. So the idea is you can model sequential agents or parallel agents. This is a sequential step. We have an M to M relationship. This is a sequential step here, but then there are two sequential steps for this for parallel events. That's something interesting. If you should read if you want to read understand this, just read that thing and then or email me if you have any questions. You can read the paper. Another case is when you want to introduce a ranker, you want to model the idea that ranking is also another decision. So if you send to your outputs to your parallel models to a re-ranking model, then that model tells you which ones it thinks are valid, and then you send those results to the final model, which is going to do the summarization. So that's how you model that. This is actually the similar one to the fuzzy example, except it's in parallel. You can imagine a ranking model that's in sequence. Let me actually do that quickly so I can show like just developing that. Then I think we can just close. So to make this a sequential model, this is a parallel model at this time, and then it's parallel is because there's no link across M1 all the M models, right? So to make it sequential, we want to add the M1 to M2 and M2 to M3. So
but I guess don't you introduce cyclicality, and then it's not an acyclic graph anymore?
No, it's just a chain. It's like 1 to 3. 2, 3,
okay,
4.
yeah, I see.
Yeah. So you'll see it. I will actually walk through it. So we want M1 to M2. And M2 to M3. So let me change this. Then this begs the question: why would we want to model a sequential model with a ranker? Like the second model will get the output of the first one. What will it do with it? All right, so so this turns it into something like a sequential model, but I think it has an issue. You can tell me what the issue might be.
Well, I mean, M2 goes, like M1 and M2 goes to rank, but they also go to M3, that rank goes to.
Yeah, so rank has double information from, like, it has output from M1, output of M2. Does it change anything? M2 gets CI and M1. M3 gets CI and M2, right?
I do note that rank gets I but not C.
Mm-hmm. That's one issue. Actually, I had not seen that. I not seen that. I shouldn't change that in the actual.
Aha, it's working.
Change that in the original diagram. Okay. So we need a link between C and rank. Yeah.
I mean, ultimately, it seems like it just depends on what you're trying to test.
Exactly.
Depending on your intent, maybe that is what you want, but it's easier to see when you have a diagram like that.
Yeah. So.
Okay, so I guess one thing you could.
Yeah, in principle, can we do sequence?
Yeah.
Maybe you can ask this question. Can we, in principle, do sequence models that have a ranker? Like, if we think about it, using this diagram, let's see if we can actually find any errors in here. Because if there are no errors, then it's like, cool, you can, and this is how you do it.
Nice.
But you can say.
Yeah, I think I'll just point at the time again.
Okay.
Yeah.
So I think we can stop here, and then if you want to talk about the more parallel scenarios, you can. Yeah, so we'll just focus on the questions, and we can go there if you want to.
Nice. Okay, awesome. Clap, clap, clap.
I guess question is there support for or intended support for like more than just diagramming, but like plugging this into some kind of automated system or I don't know. I'm just kind of speculating what you might do with this information.
Right. So let me.
Like,
okay, let me go. Let me go there. So go to the original and see this. So ICE is a library by Ott. Yeah, for interpretability, I assume you love Ott because they've done been doing a lot of this research.
Yeah, I was going to mention them as well, of course.
Yeah, they've been doing this research for much longer on weirder cases, and then when the language models came in, they had a library for it. So this is very cool. So this is how to trace language model responses in ICE. So they give you a web application page, and you can go and look at when an agent made a call, it got its sub-agents that asked questions and got answers. These answers actually inside, if you click through this, you can actually get so this is a classification step, this ask questions. There's a classification step, and then there's a classification step that is used to generate to filter for the correct paragraphs. So you can get the probabilities of the class from the classifier, and then the input here, and they're shown. So the mechanism that supports this is metaprogramming in Python. So the technology already exists for that. That's one thing. The other thing is, so basically, in principle, we can identify. So let me describe this. So what this does is that it takes, in Python, it uses Python metaprogramming to like find the program trace, because this is just a Python function calling another Python function, right? So we find the nodes program trace, and then we draw this diagram. So this is a directed graph. It's the same DAG, I think, but we just don't have each here. So the idea is we represent each of these points as a node here, and then we can automate it, because each time we make a call, the same way ICE would generate a page like this, we could generate this graph, and then that graph could be associated to the data here, this page. It could be stored in cache or something, and then visualized, or it can be shown directly to the user if you had an interface that showed it. Like if in a research scenario, I don't want to just look at an image. I could look at something which is animated, or I could look at like an output of, say, if I tag it in a certain way and then I make the language model call, I get a plot, something. That could be fun.
Nice.
Then later, we would add weights to these nodes. The idea of adding weights to these nodes means we want to find some plausible idea of the idea of information flow, first of all, and then the idea of factuality. So if you could say this node has contributed to the lack of factuality in the overall response, then what that really means is that, like in the data structure that the ranker gets or that M3 gets, if you look at that data structure, like one of the answers that came from M1 was wrong, right?
Yeah,
and
so
like that, we can identify that from the data. Maybe if we have like another method, like if we now use interpretability methods to look at the basis vectors I was talking about earlier, right? So if you have if you can hook into the basis vectors that represent truth in some dimension for whatever is being represented, then we can like graph it right here. You can just plot a graph for that particular data set, data object, or data instance, and say, cool, this is based on this model. Like if let's say you have a local model that you can use to verify things, that you want to use to verify things, or that you're studying, You know enough about that model to hook into it and say you want to hook into this layer and use these inductive biases to determine whether some of these things are true in the statement. Given the whole response, you have the inputs. These as input. You have the context. You have each subagent's response, and then you have the overall output of them. So like you want to find all of those things. So I'm thinking the research program I want to go on is like now like finding out these methods, finding out how to visualize them, how to generate the graphs in real time, things like that.
Yeah.
So
Yeah,
that's
this
the
is
next
super cool.
one. Well, that's the
Yeah. Yeah, I think this is super cool, and also just like, you know, you can imagine all the next steps with it, the weights and the actual decomposition of risk on different nodes and whatnot. A really nice setup.
Yeah.
Yeah. I think we'll have to stop here. But otherwise, thank you so much to everyone who joined here for your project presentations.